Alright, so this is the overall layout for the front panel of the LabVIEW implementation for the Intra and interface power management strategies for our work. This is a representation of the three phases, each of which are residential microgrids in their own capacity. So here we have phase A, here we have phase B, and here we have phase C. So all of these three phases, they have their individual phase-wise generation and storage, represented by PV panels on the rooftops with internal battery storages at each house, and further there are droop units also in this phase, and this is also the case with other phases also. Each of these three phases are connected with the back-to-back converter stages. So there is a back-to-back converter between phase A and phase B, and similarly between phase A and phase C, and also between phase B and phase C. The power transfer between each of these phases are represented by the arrows over here, which is up and down, and also left-right. Also, if the back-to-back converters are enabled, they are represented by the Boolean representation of the enabled signals given by these digital lights. Also, if you see over here, the phase A intraphase power management strategies and interface power management strategies are segregated for each phase. In this portion, there is an operating point setup for a particular phase. So we can set up the PV voltage across a PV panel for phase A. The PV voltage read from the device can actually be used to note down the PV current also from the IV curve, which is represented over here. So each point is actually represented by a green dot, which you can see over here. So a 220 volt is representative of 7.208 amps of current across the PV panel. So these setups are operating point. The next thing is other real-time operations, which includes the loading on phase A. So for each phase we have to decide the base load. So in this case the base load that I have taken is about 3.1 kilowatt, represented by over here as 3.1 kilowatt for load A. Also same case with load C also, and load B. Okay, so let's say that we are only catering up for the interface power management strategy. So let's say that the loading in phase A is less than the base load. So let's say we take 2500 watts as the loading in phase A. Now if this is set up, we have to also set up the PBAT max, which is the maximum battery power which can be supplied at any time, and also the P droop max, which is the maximum droop power which can be contributed. Also we need to set up the initial SOC of the battery. In this case it's given in percentage, so I have set this to 75%. So let's run this simulation and see like what happens. Okay, so what we are seeing over here is that with 2500 watts of load power, the PV generation is about 1600 watts, and this 1600 watts needs to be contributed to the P load. Secondly, 900 watts of battery power is required to actually support this load, because all of this maximum of PV power is actually being contributed to the load, so the battery has to come into play. There is no need for the P droop, which is a power from the droop unit, so hence this is 0 watts over here. Since the battery is discharging, so you can see that the SOC is going down from the original 75%. There is no current power deficiency in phase A, and there is no need for load shedding in phase A required, because load is actually considerably lower than the base load, which is over here as 3.1 kilowatts. Also note that if there is a possibility for interface power management strategy. There is some surplus power which is available in phase A. There is no PV power available, hence there is 0 watts because all of the PV power is being contributed to the load. There is some battery power which is 100 watts because 900 watts is now taken up by the load, and the maximum battery that can support is 1000 watts. So there is a remaining surplus of 100 watts from the battery, and since there is no contribution from the droop unit, so 500 watts is still available from the droop unit. Hence there is a total surplus of 600 watts. Since the load in phase A is less than the base load, there is no requirement uh, for any sort of power sharing from other phases. Hence, P requirement of phase A is 0. So this can actually be the case with all of the phases. So the interface power management strategy is one of the cases. This is for phase A. Similarly for phase C, as you can see here, the load power is exactly equal to the base load. Hence there automatically there is you can see that there is no surplus power available in phase C. So since load is equal to base load, there is no requirement for any sort of interface power management. Here in phase B, the phase load is slightly less than the base load, uh, and uh, and over here you can see that there is a surplus power of 100 watts available from the droop unit. Hence, in this first case, there is no interface power management strategy currently taking place. There is only interface power management strategy, which is trying to balance the generation with the load, or match the generation with the load. Hence, there is no requirement for any sort of interface power management strategy required by any of the phases. Here is the second case for a LabVIEW implementation where phase A has surplus power, phase C is unbalanced, meaning that the load in phase C is considerably higher than the base load, while phase B is exactly balanced, meaning that the load in phase C is exactly the same as the base load. Now here what is happening over here is that we need to see like how much power is going to be contributed by phase A and also by each of the individual DG units. So we have actually set up all the values over here. The load power in phase A is 2500 watts, which is considerably lower than the base load. In phase C, the load in phase in this particular phase is 3400 watts, which is considerably higher than the base load of 2100 watts. While in phase B, the load in phase B exactly matches the base load. So let's run this case and see what happens. So here's the case. We have deficiency in phase C, which is represented by the red digital signal over here. There is no surplus power because all of the available power from the DG units is used to cater the load as much as possible. There is an overall P requirement of 300 watts, which needs to be taken from the surplus phase, which in this case is phase A. Now let's see the situation in phase A. The phase A had 2500 watts of load power, 1600 of which was contributed by the PV generation. 900 of this P load was actually contributed by the battery. There was no contribution of the droop unit to the load, hence there was a surplus power of 500 watts from the droop unit. There was also 100 watts of power available from the battery unit. So in this particular case, where there is a 300 watt requirement from phase C, 100 watt of power will from the battery will go to phase C, while 200 watts of droop unit will go to the phase C also to make up the 300 watt of requirement. Now in the end what is happening is for this particular phase, there is no PV power available. There is also no battery power available because 900 went to this load, and the remaining 100 watt actually went to the P requirement of that phase C. The remaining 200 watts of droop unit was actually supplied to phase C, which meant that there is 300 watts of available droop power still available as surplus for this phase C. Since there is no requirement for any sort of power to be transferred to phase A, the P requirement remains to be 0, and the ratio of the amount of power to be transferred to phase A also remains to be 0 because there is no interface requirement for phase A. So this is how the interface power management strategy takes place. Also for representation, these arrows, the flow of this arrow shows that there is a power transfer from phase A to phase C. The back-to-back converters connecting phase A and phase C are represented by the green digital signals over here. Since in phase B the load is exactly matched with the base load, there is no power deficiency in phase B, and there is no load shedding in phase B, and also there is no requirement for interface power management. Hence this validates our second case where one of the phases has surplus power while other phase has power deficiency. Okay, so this is the third case for our LabVIEW implementation. In this case, one of the phases has surplus power while two other phases have power deficiency in them. So for this particular demonstration, what we are doing is that in phase A, we have set a very low phase load, which is 1000 watt, as compared to the base load, which is 3.1 kilowatt in each of the three cases. Now phase A has a huge amount of surplus power, and which can be used to balance the other two phases, which are phase B and C. For phase C, we have got the phase load set as 3400 watts, which is 300 watts greater than the base load. And for phase B, we have 3500 watts, which is about 400 watts greater than the base load. So let's run this case and see like what happens. Alright, so we are running this case. Now in this particular case, since the load is extremely small and and the PV generation is well sufficient to actually suffice the load, so only PV generation from phase A will be required to support the load. No battery or the droop unit is required to support this load. That means that there is excess power available from all the three DG units, that is the PV unit, the battery, and the droop unit. Now let's go to phase C and see what is happening. Now in phase C there is power deficiency, as we have already noted down. There is no surplus power. Now according to the mathematical formulation, we have come to know that from phase C there is a power requirement of 300 watts. Now this 300 watts is actually registered and then sent to the surplus power phase, that there is a power requirement of 300 watts in phase C. Now in phase B, similar scenario, there is a power deficiency, there is 400 watts of power requirement over here. So overall the surplus power has to supply 400 plus 300 watts, that means 700 watts in total. Now considering that there is 700 watts of power to be delivered to the power deficient phases, 500 watt of that power deficiency will come from the PV source, while 100 watt will come from the battery source. Since the droop unit is not required, there is sufficient power available in phase A from the droop unit, and there is 900 watt of power available from the battery unit. Overall there is 1400 watt of power available in phase A even after the interface power management. For demonstration purposes, you can see that there is power flowing between phase A and phase C, and there is power flowing between phase A and phase B. Since the all the three back-to-back converters, two back-to-back converters will be used. One is the back-to-back converter between phase A and phase B, and the other one is between phase A and phase C. So the enabled signals uh, are enabled. So this demonstrates the case where one of the phase has surplus power while other two phases have power deficiency in them. Alright, here's a case number 4 where two of the phases have surplus power while the third phase has power deficiency. For the demonstration purposes, I have shown that phase A and phase C have power surplus while phase B has power deficiency. Uh, Power surplus can easily be set by having a very low power load requirement in each of the two phases which need to be in power surplus, while the third phase has loading requirement greater than the base load. So let's run this simulation and see like what happens. Okay, so in this case, what is happening is that in phase A, the load is very small, and only PV generation will be required to actually support the load, which is same case in phase C also, because P load is same as in phase A. Hence, there is power surplus in both phase A and phase C. While in phase B, if you can see, there is no surplus power because all the available power from the DG units is used to support the load. There is a power requirement of 400 watts. So now what will happen is since the loading in both phase A and phase C is the same, they're gonna share this 400 watts that is required by phase B. So you will see that the surplus power available in both the phases will remain the same as 1900 watts because they both have the same loading requirement, and the PV generation and the battery and the droop units have the same available powers as in phase A. So for the demonstration purposes, you can see that the power is flowing between phase A and phase B, while there is power flowing between phase C and to phase B in order to support the power deficient phase. Back-to-back converters between phase A and phase B will be enabled, while the back-to-back converters between phase C and phase B will be enabled. Alright, so for case number 5, we are demonstrating that all of the three phases have power deficiency and there is no surplus power available. So in this case, what we're trying to do is that all of the phases, phase A, phase B and phase C, will have load power greater than the base loads. For demonstration purposes, I have set phase A as 3500 watts, which is 400 watts greater than the base load. For phase C, I will be setting this to 400 watts, which is about 300 watts greater than its base load. And for phase B, we have got 3500 watts, which is 400 watts greater than its base load. So let's try to run this case and see like what is happening. So in this case, since it is expected that all the phases have power deficiency, all the signals denoting power deficiency will be turned on, as you can see, phase A, phase B, phase C and phase B. Also you see that there is load shedding imminent signal also in all of the three phases, since there is no way in which all of the three phases can be balanced in this case. So also for demonstration purposes, there is no power transfer for between the phases in this case. No back-to-back converters will be enabled, and hence there will be a requirement for the load shedding to take place in this case.